Okay, so as I promised you guys, while we were doing the last unit, I said, let's get really ready for this next test because it's probably the toughest one of the year. Things will get easier. Well, today, we're going to try to find out if that's true. Okay? Whether or not I was lying to you or whether or not this truly does appear like material that's easier to grasp. So we're going to start today with a little pop quiz, but not really. I'm going to ask you a series of questions that pertain to the next topic before we even learn anything about the topic to see whether or not you would do okay without me. Most of you probably would agree that in the last unit, trying to do some of those problems from scratch on your own without me may have been tough, right? But let's see what happens here. So I'm going to set up the first scenario for you, and the question will appear on there. But before I do, let's say that Eric here finds the love of his life and you buy a house, right? You're up in the attic of the house, okay? And the house is kind of old, so maybe the wiring's a little faulty. And while you're up in the attic working, you smell smoke. And you notice that down below you, the first floor is on fire. And you're trapped up there. And you look around, and the only two exit points are those two windows that are facing the front. One of the windows, if you were to jump out of it, would have you land on the cement. The other window, which is also accessible, would have you land on the grass. Now, both windows are exactly the same height above the ground. So the question one is, would you rather jump out of the window onto the grass or onto the cement?
On the grass.
On the grass. Okay. Question two. I made Gabriel dive off of our diving board. And it's not a little one, it's a huge diving platform like they use in the Olympics, right? Would you rather dive off that platform into the water or into the wet cement?
Water.
Into the water. Oh, we're 2 for 2. And this is not going well. I thought I'd really get you guys by now. Would you rather jump onto a bed, Natalie, would you rather jump onto the bed of nails or the bed of feathers? The bed of feathers. You guys want this to count as a quiz?
Yes.
Okay. I would never make this count as a quiz unless you guys were able to do the hard part. That was easy, wasn't it? We didn't have, everybody would consider those responses obvious, I hope. But the physics explanation as to why is not so obvious. Okay? So when you try to consider, why is this happening? In every one of those scenarios, we start with Eric. Does everyone agree that he was jumping from the same height above the ground, right? Same gravity, so same acceleration, same distance that he's traveling, same V initial, which would mean the same V final, right? So when he hits the ground, he's going the same speed both times. The question becomes, why is it nicer for him to hit the ground when it's the grass as opposed to the concrete? Then we go to the next scenario. Why would Gabriel rather hit the water than hit the wet cement? Same height, same V initial, same V final, same impact in all cases. But there's definitely something different about the impact of those two things, right? The bed of feathers, the bed of nails, right? Same thing. What physics factor helps us to explain why one choice is the obvious better choice than the other one? What do you think? Come on. Just use your common sense, Natalie.
You like the texture of the
the texture, kind of like what we used in the coefficient of friction. Okay, what about it? What about, so you're saying there's something having to do with the surface that matters, and I agree. But what is it? It's actually not a new variable like mu was, like when we learned about the coefficient of friction. It's easier than that. It's softer. And what is softness going to do for us?
Cushion.
Cushion. And what is, so now you guys are starting to think a little bit about the egg drop too, I hope, right? Why we would have done something like that yesterday. What were we trying to do for our egg? I mean, it comes up later in our presentation, but just think about that as you're trying to figure out what's happening here. Read this line right here. It says, in every case, the impact is the same because these things are the same. What's the one thing that's missing that might be the most important? Think about our old equations. The time. Oh, wow. Well, how would that affect things? So everything leading to the ground is the same, right? But then, when do you feel an impact? Because today that's what we're talking about, right? Just like the egg did yesterday, we dropped the egg. When does the impact start? From when you approach the ground till you come to a stop, right? So the time might matter. What does having a cushion do for you? It gives you more time to do what? To stop, to slow down and stop, right? And if I have more time, that affects things a lot. As you're going to see here in a second. The name, so I've used the word impact a couple of times because that's the everyday word. In physics, for some reason, we give a 50-cent vocabulary word that's really not necessary because this word, impulse, means the same thing. So the impulse is what we're talking about. The impulse is the same on you, whether Eric jumps out onto the driveway or he jumps out onto the lawn. What ends up happening to him is he goes from whatever speed he was going to a stop, right? But what Beatrice told us is the one key element that might have been missing is the time, and it ends up being the key factor in all of this. Here's how it works. In each case, you see how I made the graphic for the eye exactly the same size font? Because eye doesn't change. Whether you jump onto the bed of nails or the bed of feathers, eye is eye, right? But if we can figure out how to make T get bigger, it makes the force of impact on us get smaller. If T is really, really small, like when Eric hits the concrete, does the concrete take a long time to make him stop? No. It's very, very rigid, and so the stop is abrupt. The shorter the stopping time, the bigger the impact force, right? So a long, long time ago, before they had airbags and stuff, what would they do to your steering wheel? They would put like foam padding around it, right? They would make the padding on the steering wheel something that if your head were to hit it, the padding would compress, and what would that do to the amount of time it took for your head to come to rest? It would make the time get bigger, which in turn then makes the force on you get smaller. And what's the physics word for pain? It's force, right? Forces are what cause injuries, what cause pain, right? So if you want to make this get smaller, you got to make this get bigger. When Gabriel's jumping into the cement, the reason why it's not fun to jump into the wet cement pool is because that wet cement isn't going to take a long time to make you stop. You're not going to get in very deep, are you, before you're already stopped? And that kind of impact would probably cause injury because F would get really, really big. So even though I stays the same, the product stays the same, we try to make T get bigger. In fact, it's why all of the safety features in your car exist. Because if you're hitting a wall in your car, let's say you hit a barrier going 50 miles an hour, the impact going in stays the same. The impulse is the same. this guy. So if we could make this get bigger, this gets smaller. How do we do that? Well, your car is actually designed to do that. Let me pick on somebody else. We're gonna get to that. Nick, let's say that you go to engineering school, you come out, you're very, very, very good with structural mechanics and with all of the material stuff. So you develop this new structural material that's so rigid that if somebody takes their car, drives to the mall, and some annoying imbecile swings their door open and hits your car, no door dings, no dents, no nothing. You've built the ultimate car where 20 years from now it's going to look brand new. No damage. You decide that you're going to build a car and market the car. Do you think it's a good idea? Do you think, first of all, do you think that we have the technology to build a car like that, one that won't dent even if you smack it into a wall going 50 miles an hour? We do have the technology. Good. We can do that. Would you want to be driving in that car? No. It's a death trap, right? You would never want to drive in a car like that. In fact, in 1973, Mercedes-Benz came up with a technology that was so powerful, that was so great, that they decided to not even enforce the patents on it. They got patents on it, which means that it was their proprietary stuff and that nobody could use it if they didn't want them to. And they felt like it was too important and they just let it go. This technology is called the crumple zone technology. And what Mercedes-Benz did is they designed the front of your car to crumple up like an accordion. So your car is actually designed to dent and ding and actually get pushed in. Because the longer we could make the time that it takes for your accident to happen, the smaller the amount of force on all the passengers in the car. It's the difference between being able to survive the crash and not. How many of you have watched a NASCAR event where you've seen a guy crash into a wall going 200 miles an hour and get up and walk away? You've seen it, right? What does a car look like when they're done? There's like nothing left of it, right? The whole idea is, as this car is slowing down to a stop, it's disintegrating before your eyes. You're looking at this thing and there's like nothing left at the end, right? Now, obviously that takes this idea of making F get smaller by making T get bigger to an extreme, right? Because then what happens? Every time you get into any little accident, what happens to the cost of the repairs? They skyrocket, right? So you have to find some kind of balance, some kind of happy medium. So if you don't think that the automobile industry, like every other industry, doesn't put a monetary value on your life and your safety, obviously you've miscalculated. They do. So they're going to make a balance between keeping your car safe and making it cost effective to keep your car running. Right? You don't want your car to always be falling apart with every little thing that happens, because if it does, then you're constantly going to be costing your insurance company money. On the other hand, if you hit a wall, you don't want it to stay looking perfect like the cars of the 1960s, because if it does, all of the force will be transferred into you, because the time that it's going to take for your car to stop when it hits something is going to be really small. So you want that flex. In fact, cars flex so much nowadays that we have to put your engine on rails. So think about that, right? If front end of my car is smashing like an accordion and there's this big hunk of metal called my motor that's sitting there, I don't want my motor on my lap, right, as this thing smashes. So they put your motor actually on rails so that when you smash into something, if it compresses enough, the motor automatically gets dislodged and gets driven underneath the seats via these rails. So your seats will kind of be up, and you've probably seen cars that look like they're buckled up like this. That was designed to happen on purpose. So the motor goes underneath you instead of the motor coming at you and crushing you. Does that make sense? So all of that stuff comes from one little tiny physics equation right there. I equals F times T. And it's really easy. Now, does everyone see the physics that I'm talking about? It's pretty easy. If only life was this good, a month ago, right? But this isn't like F equals ma. This one truly is really that easy. So the thing you have to remember is T is the main factor. In order to make F get smaller, you can control T. You can control that impact time by adding padding or cushioning. That's what you were trying to do with your egg, right? If we could make the time that it takes for the egg to come to a stop, come to rest, get smaller, then the force is going to get really big, egg's going to break. If we make that time get bigger by cushioning it, we have a chance for the egg to survive. Because the force will become smaller. All right. So now we kind of know the answer to this question. Why do we do the egg drop? We were trying to see who would effectively be able to increase the impact time by the most amount, therefore decreasing the force acting on the egg and keeping the egg safe. Moving on. So there's two parts to today. In part 2, we're going to talk a little bit about momentum. And look at what I call momentum. Momentum is moving inertia. That's the best definition I can think of in very few words to describe what momentum is. And by the way, I searched for a long, long time for my graphic. So if you pay close attention to the picture, the next question, the answer to the next question may pop out of that. And my question is, well, I think I have it on the next slide. What does an object need in order to have or increase its momentum? Does it need to be accelerating? Think about inertia and moving inertia. What do you need to have moving inertia? You need to be moving. Good. So there needs to be a velocity. And what else? What? I heard somebody say mass. Good. The more massive something is, the more inertia it has. That's why I put the boulder on there. The boulder chases the guy down the hill. The more massive something is, the more inertia it has. The faster it's going, the more inertia it has. So what do you think the two things are going to be that are in momentum? Mass and velocity. That's it. So I put a Mack truck on the graphic to show you that this Mack truck, even though it has a ton of mass, has no momentum. So if there's like a little bug flying around the bus right now, or around the truck, I mean, that little bug has more momentum than the Mack truck, because the Mack truck right now has no momentum. Now, if this truck starts moving even really, really slowly, it's going to be really, really hard for the bug to maintain the same momentum as the truck, isn't it? Because what does the bug have to do in order for it to have the same momentum as the truck? It has to make up for how much more mass the truck has than the bug, right? So even if this truck were going really slow, 1 meter per second, the little bug that was flying around might have to go, because the truck's about 400,000 times the mass of the bug, it'd have to be going like 400,000 meters per second, or roughly 800,000 miles per hour, just to make up for the truck going about 2 miles per hour. Does everyone see how that works? All right, because we're going to be testing that out later. So here's our equation, and yes, momentum does, when you're writing this on your note card, special note, it's number one, it's lowercase p, and yes, unfortunately, that is the symbol for momentum in all physics textbooks, mainly because M was taken, right? So in order to not confuse our work, we introduce a new variable. The momentum P equals mass times velocity. The two variables that we identified were going to be in momentum. So far, so good? Yeah. The units for momentum, then, are going to be in kilograms times meters per second squared. Which, if you look at those units, unlike newtons, which are kilogram meters per second squared, kilogram meters per second which I think I might have misspoke just now, but kilogram meters per second there is no shortcut for that. Like when we call the Newton big N, we substituted it for kilogram meters per second squared. There is no substitute for this one. You just got to write it out. So there's no shorthand. But if you look at that, and then we go backwards, look at the units for impulse. They're the same. Because impulse is newtons times seconds, which are, if you simplify it, kilogram meters per second squared. That leads us to our last thing that we're going to learn today. And that is how impulse and momentum are related to each other. Because they're definitely related. So here we have a diver going into the pool, right? What happens to the diver as soon as he hits the water? And all of you have jumped off of a diving board probably into a pool. And if not, you've at least jumped off the side of the pool into the water. What happens to you as you enter the water? You slow down, right? You slow down immediately, don't you? Because it's harder to go through the water than it is to go through the air. So as soon as you hit that water, you slow down. So as soon as that water puts a force on you over any amount of time, which means you're having an impulse, right? Impulse is force times time. So as soon as that force acts on you for any amount of time, what happens to your momentum? Well, in the case of the diver, it decreases, right? Your momentum goes down because you slow down. So your velocity changes. What if I change this idea and I put Sam on rollerblades, and she's standing there like this, and I apply an impulse. I push her in the back with a force for some amount of time. What's going to happen to her then? She's going to speed up, right? As I push her, she's going to go faster and faster and faster. And what does that mean? So in that case, her momentum went up. So all you can tell about this question is there's definitely a relationship between when an impulse is applied and what happens to your momentum. And it's actually a pretty simple one. I think I have it here. What we've determined is your velocity must change. So in the case of the diver going into the water, the velocity went down. In the case of Sam on her rollerblades, her velocity went up. It doesn't matter. All we're saying is this. If an impulse is applied, then there's going to be a change in momentum. And if you break that down, and this goes on your note card, by the way, both I equals change in P goes on your note card, and F times T, which is what I is, right, equals change in P, which is N times a change in V. You can rewrite this on your note card if you want to as what we always write our change in, which is V final minus V initial, right? Because if you leave that, it makes it look like it's one variable, and really you need both to get change in. So far, so good? Last step. I have this little disclaimer here, but wait. If you look at this, it's kind of weird, because if we take F times T equals M times change in V and we solve it for F, so we get F by itself, we end up with F equals M times change in V over T. What is this? What's the change in V over T? Second day of school. Somebody just said it. It's acceleration. Does everyone see that this is just F equals MA? F equals M times A. It's a whole new way to think about Newton's second law. So we're breaking Newton's second law up into ideas like impact and momentum, and talking about it that way, but it's not anything new. Questions? This is the way, this top way here is the way that you should put it on your note card. Because it'll remind you that impulse equals a momentum change. Last question from me to you guys, and we'll be done for today. What's the impulse acting on you as you're cruising down I-90 going 55 miles per hour towards the city? If your car's 1,000 kilograms. 1,000 kilograms, 55 miles per hour is about 23 meters per second. So you're going 1,000, you've got a 1,000 kilogram car, you're going 23 meters per second, you're going straight east down the Kennedy towards the city. What's your impulse? What's the impulse acting on your car? 23,000, right? Wrong. Why is it 0? Very good. How much is my velocity changing if I'm cruising along at 23 meters per second going towards the city? Oh, isn't that changing at all? Guess what then? That means that there is no impulse. Right? Now, are there forces acting on my car? Yeah, but the net force is 0. So the net impulse is 0. Everyone understand how that works? You are looking for a change in velocity in order to be looking for an impulse. No change in velocity, no impulse. Okay. All right, we're done for today.